Welcome. Now for helium. Helium is one that we can't solve exactly. So I'm going to start with one that we can solve exactly, and that is the hydrogen Hamiltonian. Here's the Hamiltonian and the potential energy part of the hydrogen atom. That's the one we just looked at. Here's the hydrogen Hamiltonian with a kinetic and a potential part. And then here's the helium part, a helium version. Well, you know what? We're going to have two hydrogen-looking things. And they're both going to fill the 1s orbital. That's why helium is relatively inert and hydrogen is very reactive. Here's the first electron's kinetic, the second electron's kinetic. So we lump those together with this kinetic bracket. And then over here is the potential energy. Okay, we're used to E squared over 4 pi epsilon 0 r, but what's this 2 all about? Well, how many protons are in the hydrogen? 1. How many protons are in the helium? 2. So that's why we've got a 2 up there, and that 2 protons are attracting each one of the electrons. So we're all done, right? Here's the Hamiltonian, here's the Hamiltonian, and I'm going to put everything in atomic units. Atomic units make the presumption of the following. The electron mass is equal to 1. So the mass is all based on the electron. The elementary charge, the value of the charge is equal to 1, which is the charge on a single electron. The reduced Planck's constant, which is h bar, that's the constant over 2 pi is what that bar indicates, that's equal to 1. The Coulomb constant, we've already dealt with over and over again, is 1 over 4 pi epsilon 0. That's the permittivity of free space, and this gives it the spherical nature. Here we go. I'm going to plug those things in. It just becomes 1/2, 1/2, 2 over R1, and 2 over R2. So we're done. Da, 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 da. Nope. Burr, burr. What have we forgotten? What have we forgotten? We have forgotten electron repulsion. Electron repulsion has 2 electrons and the radius or the distance between the 2 electrons. That's what that R12 there is. So that's going to be vector 1, which is referenced from the nucleus, and R2, which is referenced from the nucleus. We're going to subtract those 2 vectors and we'll come up with a third vector. I guess I should have put the little arrow over this one too, the R12, but that gives us the Hamiltonian. All of this is fine. We can solve this, no problem, but this is not easy. This throws in a ringer that does not allow an exact solution to the helium atom. So this looks like what we had before, except for the Z. What is the Z? That's the effective charge, and it is 2 because it's a 2-proton nucleus. Now, we're going to try to figure out this function over here that we can't deal with. This is the one that's the tricky one where we've got the R1 and R2, and we've got this capital psi function of R1 and R2, which is equal to the product of the psi function lowercase 1s, psi function lowercase 1s. Those 2s have opposite spin orbitals, so they fill the shell, and then here's the vectors. So each one of those has can be a variable r that comes up with these 2 psi functions. Now, do those have to be equal? No, they don't. So the electrons don't have to be the same distance from the nucleus. Then we come up with this, which we already did on the last page, and here's the difference of these two vectors, which is the distance between those two. And then I come up with this. Psi of side 1s r equals what? Z cubed, that's the 2 proton effective charge, over pi. Take the square root of that, and then you multiply it by base of the natural log with an exponent of minus zr. Now, does that take some explaining? I think so. Explain it and then try to understand it at the same time, and maybe we can both get there. The two electrons together, just those two, introduce some quantum mechanical principles that we didn't have to worry about with hydrogen. With hydrogen, we just kind of let it go and let the Coulomb potential do its work, and everything was fine. Two electrons are present, and those two electrons are the same particle type. They're the same mass, same charge, but they both occupy the same space. And the electron is a probability distribution, so what problem does that cause? Something says that the Pauli exclusion principle gets involved here. Well, let's look at it in a simple way. An electron has more than just a spatial property. Now, with hydrogen, spatial property was plenty. We didn't have to worry about this property called spin, and whether we want to visualize it as the particle spinning around like a top, or we just want to use the term spin, it has a definite direction to it. And it so happens that the electron, if it has spin up, which we'll just say there's two kinds of spin up and spin down, that if one is spin up, the other has to be spin down. And even though the two electrons are identical, one of them has to have one type of spin and the other one has to have the other type of spin. They can't both be spin-oriented the same way. Now, who says so? Well, Pauli. Pauli exclusion principle says that they can't do that. They can't both have the same spin. Now, is this a classical idea? No, it's 100% quantum mechanical idea. So this we cannot relate to in real life. And we're not going to be able to relate directly to items in our macro world that have this Pauli exclusion principle that occurs. But we apply the Pauli exclusion principle and the math works. If we don't apply that Pauli exclusion principle, then it doesn't work anymore. So we're going to have to live with that. Now, that complicated looking equation, we're not quite there yet. We had to just introduce this idea, and we'll call it a rule of anti-symmetry, meaning they're not the same. Anti-symmetry. Symmetry would mean they're exactly the same. Anti-symmetry says that they're not the same, and that's built in. They have to be anti-symmetric. So which one goes spin up and which one goes spin down? I don't know. And it really doesn't matter. One's spin up and one's spin down. Now, is there a probability that they could both be spin up or a probability that they could both be spin down? They have a probability of 0 at that point. And they have a non-zero probability outside of that, of being a spin up or spin down. That's just a bunch of garbage, isn't it? The way it comes out. We have to put these into math symbols so that we can sort this out and not just talk about them with some strange analogy. Well, I just said that they couldn't have the same spin. In other words, they're anti-symmetric. But that would be if the spatial orientation were symmetric, meaning the radius. If the radius from the nucleus is the same, then the spin has to be antisymmetric. Well, what if we make the spin symmetric and they're both spin up? Then the radius has to be antisymmetric. So let me see, we got a 1s hydrogen shell and a 2s hydrogen shell. And if they both have the same spin, then one of them's got to bump up to that higher energy level. That's the uncertainty about all this kind of stuff. And that's why the math is an approximation. Because we're just dealing in probabilities now, we're not dealing in certainties. This is the land of quantum mechanics. From this point, we're going to move on to our first calculation, antisymmetric calculation, and also symmetric calculation. But we're going to do this in another video. I just wanted to finish this thing off to show you where things are headed and to prepare you for the confusion factor that's going to come up. And this is hopefully going to reduce the confusion factor for you and for me.